Every road you drive on was compacted by a machine most people never think twice about. But inside that drum, something is happening at 4,000 impacts per minute that most engineers took decades to fully understand.
The oldest assumption in compaction is simple. The heavier the machine, the better the result. And weight does matter, but only at the surface. Static pressure compacts the top layer while deeper layers remain largely untouched. Everything looks perfect from above, but beneath the surface a weak zone still exists, waiting to cause problems years later. This is why roads built with heavy equipment can still crack, deform, and develop potholes long before their design life is up. The problem was never mass, it was penetration depth. To change the structure of material below the surface, you need energy that travels downward, not pressure, energy. And those are not the same thing. The solution is hidden inside the drum, and it is more precisely engineered than most people would expect from a machine that rolls back and forth over dirt. At the center of the drum is an eccentric shaft. It is a shaft with an unbalanced mass bolted to it, deliberately offset from its axis of rotation. When a hydraulic motor spins that shaft, the offset mass generates centrifugal force. That force is transmitted outward to the drum at high frequency, causing the drum to lift off the surface and impact it again in a rapid, controlled cycle. On a modern, high-frequency roller, this happens up to 4,800 times per minute. Each impact drives a compaction wave downward through the material. The soil particles or aggregates shift, rearrange, and lock together more tightly. Air voids collapse. The load-bearing structure of the material builds from the bottom up, not the top down. That is the fundamental difference between static compaction and vibratory compaction. The shaft is only part of the system. What matters operationally is how two parameters are set: frequency and amplitude. Frequency is the rotational speed of the eccentric shaft, measured in vibrations per minute. Higher frequency means more impacts per meter of travel, which allows the roller to move faster while still hitting the minimum threshold for effective compaction. The industry standard for asphalt is a minimum of 10 impacts per foot. Exceed that threshold and the material locks up. Fall below it and the surface ripples. Amplitude is different. It is the physical distance the drum is displaced from its neutral position by the rotating eccentric. In simple terms, it is how hard each impact hits. High amplitude drives energy deeper into the material, which is what you need for thick lifts or dense aggregate. Low amplitude is used for thin layers and softer mixes, because high amplitude on a thin asphalt overlay will fracture the aggregate particles rather than compact them. These two parameters work against each other. On a standard roller, low amplitude allows higher frequency. High amplitude requires slower rotation. The operator has to choose the right combination for the material and layer thickness they are working on. Get it wrong and the surface either fails immediately or fails invisibly, with a weak zone buried underneath a smooth finish. Modern machines solve this with a dual amplitude eccentric. Two eccentric masses are connected on the same shaft. By reversing the direction of rotation, the secondary mass repositions itself relative to the primary mass, either adding to or subtracting from the total eccentric moment. This switches the machine between high amplitude and low amplitude without stopping or changing any physical components. Volvo's DD128C runs the highest production frequency currently available at 4,800 VPM in low amplitude mode. Manufacturers including Bomag, Ham, Sakai, and Dynapack all offer similar dual amplitude systems. The practical result is a single machine that can work on granular base layers in the morning and thin asphalt overlays in the afternoon without any mechanical adjustment between jobs. The way a road roller moves is as deliberately engineered as the way it compacts. There is no conventional gearbox, no mechanical gear changes. The machine uses a hydrostatic transmission, where a diesel engine drives a variable displacement hydraulic pump that sends pressurized oil to hydraulic motors at the drum and rear axle. Speed and direction are both controlled by varying the flow rate and direction of the oil. The machine can move forward, stop, and reverse without any gear selection. And there is no throttle pedal. This is one of the most unusual details about these machines, and it is entirely intentional. Compaction quality depends directly on maintaining a constant travel speed. Any acceleration or deceleration changes the impact spacing across the surface. The operator sets a target speed using the travel lever, and the system holds that speed regardless of terrain resistance. It removes one of the most common sources of operator error. A road roller also does not steer by turning its wheels. Instead, the machine bends in the middle through a central articulation joint. The front and rear frames pivot relative to each other. The reason is the drum. During compaction, the drum must maintain full, uniform contact with the surface across its entire width at all times. If steering were achieved by angling the drum, one side of it would lift slightly in corners, leaving an uncompacted strip. The articulated frame solves this completely. The drum stays parallel to the surface through every turn, and the compaction pressure stays uniform from edge to edge. If you want to understand how this kind of machinery actually works, subscribe. The machine generates thousands of impacts per minute into the ground. The challenge for engineers is keeping those impacts in the ground and not in the person sitting in the cab. Prolonged exposure to whole-body vibration is a documented occupational health risk. It causes cumulative damage to the spine and joints, accelerates fatigue, and reduces concentration over the course of a shift. The condition is called whole-body vibration syndrome, and it is regulated in most countries with daily exposure limits. In the EU, the action level that triggers mandatory health monitoring is 0.5 meters per second squared of vibration dose. The engineering response is layered. Rubber vibration isolators are installed between the vibrating drum assembly and the roller's main frame, absorbing a significant portion of the oscillation before it reaches the chassis. The cab is mounted on a separate isolation system. The operator's seat has its own integrated suspension, tuned to the operator's weight. The result is that the drum can run in aggressive compaction mode, while the person controlling it experiences a fraction of the actual vibration energy being delivered to the ground. The newest development in this field changes what a road roller actually is. Intelligent compaction systems equip the roller with accelerometers in the drum, a GPS antenna, and an infrared temperature sensor. The accelerometers measure how the drum is reacting as it contacts the material. As material stiffens under repeated passes, the drum's response changes, and the system detects this in real time. The operator sees a color-coded map of the site updating live, showing which areas have reached the target density and which still need additional passes. More advanced systems adjust vibration frequency and amplitude automatically based on what the sensors are measuring. The roller is no longer just following a predetermined pass count. It is responding to the actual condition of the material beneath it and stopping when the work is done. Pass by pass, zone by zone. The U.S. Federal Highway Administration has been promoting intelligent compaction on public road contracts since the mid-2000s, and the technology is now standard on new machines from Caterpillar, Bomag, Ham, and Dynapack. A retrofit kit for an existing roller costs between $50,000 and $75,000. The payoff is fewer passes, less fuel, and a documented record of compaction quality across the entire surface area of the project, which is increasingly required on government contracts. Despite how similar they look from the outside, there is no universal road roller. Smooth drum rollers are used for asphalt compaction and finishing. Pad foot rollers, also called sheep's foot rollers, have protruding pads on the drum surface that punch into cohesive soils like clay, achieving compaction at greater depth than a smooth drum can reach. Pneumatic tire rollers use multiple rubber tires to apply a kneading pressure across the surface, which seals the material and produces a denser, less permeable finish. Tandem rollers carry two drums and are used for the intermediate and finish rolling stages on asphalt paving. Using the wrong type for the material is not just inefficient, it can actively damage the surface. High amplitude vibration on a thin asphalt overlay will fracture aggregate, A smooth drum on cohesive clay will seal the surface and trap moisture rather than compacting the material beneath. Costs reflect this specialization. Entry-level single drum rollers start at around 50,000 euros. Mid-range vibratory tandem rollers run between 120,000 and 250,000 euros. Heavy-duty soil compactors and combination machines reach 500,000 euros and beyond. High-end models with intelligent compaction, climate-controlled cabs, and telematics push further still. Every road you have ever driven on passed under one of these machines at some point in its construction. The quality of that compaction, invisible once the surface is laid, is what determines whether that road lasts 10 years or 30.